Hi guys, good morning. So this is Dr. Supriya Suresh, who will be handling your subject Fundamentals of Machine Learning with the course code of IC 71. To begin with machine learning, in our day-to-day activities, we do see a lot research work going ahead with machine learning, deep learning, artificial intelligence. Yes, so all these terms they do have an interrelation between each other. Okay, so to begin with, if we consider, as per your syllabus, the textbooks preferred are from Tom M. Mitchell. It's a machine learning introduction to machine learning. It's an Indian edition, 2013, McGrew Hill Education. And the second textbook is the Atham Alpidin Introduction to Machine Learning, second edition, MIT Press. If you want to go ahead and check out the series of NPTEL Swayam, so there's one from Dr. Sudeshna Sarkar, Introduction to Machine Learning. A lot of important contents are being well. Um, so you could go ahead and read them for an additional information. Okay, and your module one, it is described here with introduction, a brief introduction to machine learning. You have your supervised, unsupervised learning, reinforcement learning. They are the different types of machine learning. The well-posed learning problems, designing a learning system. How do you make a system learn? Okay, so with the help of the target functions, or with the given input instances, how are you going to design a learning system? The perspective and the issues with machine learning, the current issues that the machine learning or the problems related to machine learning. Okay, and with respect to concept learning, okay, concept learning task, concept learning as a search. There are a few algorithms that have been involved in it. One is the finders algorithm and the candidate elimination algorithm with the version space and inductive bias. This is about your contents with your module one. To begin with the session today, let's go ahead with the introduction to machine learning. Okay, this is your module one and it begins here. Introduction to machine learning. What is exactly machine learning? Is there any definition that states about machine learning? Yes, there's one definition that has been stated by Tom and Michel in 1997. Okay, and the definition states like this. See, a machine is said to learn from experiences with respect to some classes of task and a performance measure P if the learner's performance at tasks in the class as measured by P improves with experience. I know the definition seems to be a little difficult to understand or to memorize. Okay, let's go relate this to an example so that it will be really very helpful for us to not to by heart but to at least get to know what machine learning is. And let me consider an example, like I'm the initial beginner in cooking. I don't know. I really don't know how to cook. I don't know the steps that they follow to cook. What do we do? If you are the initial, right, maybe your parents would not have I mean, till a certain age they don't let you go inside the kitchen on your stoves and you do it, but after certain time when you're more flexible with it, they tell, okay, you can switch on the stove and you can start doing small things, right? Like now example here is I have to prepare a dessert, okay, some sweet, I have to prepare a dessert and I really don't know how to do it, so I ask my mom, can you let me know the steps that you perform? So she tells me, okay, if you want to start your dessert, you have to have these ingredients. Okay, so first I have to get to know what are the ingredients for it, and the next is I have to know the procedure to perform it, because without the procedure it's difficult. If I add sugar maybe at the beginning of it or the end of it, or you don't know where at what point of time that you have to add it, because when I tell certain ingredients like ghee, sugar, you might have some jaggery, a little bit of pinch of salt, maybe a lemonade, you might need all of these ingredients, right? So you don't know at what point of time that has to be added, so you need to know the procedure as well. So when you go ahead with these procedures, so you also need to know how you started, okay, which kind of a bowl you need it and how do you switch on the stove. That's what entirely we need to know the procedures, and I can call it to be as a set of tasks. Okay, so I need to know the tasks of it. Now I have performed, okay, since my mom gave me the set of tasks that I have to perform, and at the given instance of time she told me to add all of these things. I've added it and I've prepared my dish. Okay. After preparing, there should be someone who should tell me, right, whether I've prepared good or not. Okay, there should be someone. There should be a evaluation, right? There should be someone who has to evaluate the dish and tell them, okay, this is what it is. Oh, in that case, okay, I'll ask my mom. You come and evaluate it and tell me how does it. Okay, for the first time, maybe I might feel that. Okay, I could have done better. Okay, again I'll try it for the second time, again I'll try it for the third time. As many number of times I perform right, I would try to be an expert in doing that particular dessert, right? This is how we also do it. First time when we do a mistake, or second time, we try to rectify that and we try to make sure that we try to do it perfectly, right? So based on experiences, okay, the performance metric actually improves, right? So this is what your definition also states. A mission. Let's consider, are we human beings when we are trying to do that? How why could not we try to check the same with the mission, right? So a mission is set to learn from experiences. Yes. With respect to some classes of tasks, now I'm giving the same classes of tasks to the mission, and there is a performance metric P. So performance measure, someone is going to do was my mom with respect to me. So even we will measure it. Okay, if the learner's performance at task in the class as measured by P improves with experiences, so obviously the performance metrics is going to be improved, right? As and how he gains more experience, right? So here define learning is with respect to the task, so it's going to be specific classes of tasks. So let me just annotate here for your reference. So define learning is with respect to tasks, it's basically the specific classes of tasks, as I told you, like the list of tasks that I have to know whether learning is happening or not. Okay, you first need to find a performance criterion, as I told you. When we're going to go ahead with the learning, as we have to measure certain things, you first need to define the performance criteria. Okay, whether the dessert is a sweet, okay, what in case, if rather than adding a sugar I add a salt, because my mom would have told me add something which is white in color, which is crystal like, you also get crystal salt, right? So in that case, if I add salt, okay, how would it be? Okay, so you need to get to know the performance criterion as well. And with experiences, obviously the performance will increase or it will improve, right? So this is what I have written here. There's one more definition. We call it to be as inductive learning. Learning to improve the performance based on experiences is known as inductive learning. As as whatever we have defined so far, okay, what is learning? It's basically that we are trying to see that we are improving ourselves, right? So learning to improve the performance based on experiences is known as inductive learning. Okay, as I told you, this is one of the example that I've written over here for understanding. Example, suppose as I told, I'm a beginner in cooking. First we need to identify the specific classes of task. For example, while preparing a dessert, we first need to identify the ingredients and the procedure to cook. Okay, with the procedures followed, we start a learning process. And as and when we are learning, the preparation is to be quantified with the performance metric, the task of the desert. Okay, the taste of the desert, I'm sorry. The taste of the desert. Obviously, based on the multiple trials, as we gain experiences, the performance increases. So similarly, there's a learning to recognize the spoken words, learning to drive an automated vehicles, classifying new astronomical structures. So all of these things are with respect to learning. And this is what your definition of machine learning is with respect to inductive learning. To go ahead with, everybody tells, okay, machine learning, artificial intelligence. From where did it start? What is the history of machine learning? So when we look at the history of machine learning as mission, okay, what is a mission basically? It is an intellectually capable, a mission that is intellectually capable as much as humans basically inspired a lot of researchers. So the first machine learning system was developed in 1950 by Samuel working at an IBM. Okay, he developed a program to play checkers. Checkers is a game where you start playing with the positions of the particular game. Okay, so you observe the positions at which okay, observe the positions at the game, learn the model to produce better moves for the mission players. Okay, it was learned from experiences. So as and how you started playing things, right? So the first time you would not know what are the rules and regulations of the game. So once you get to know the rules and regulations of the game, let's consider a simple example of the chess game. You have all the pawns, right? So when you're making a move, you first need to know, okay, what each and every, what does the horse pawn do, or what does the king, the queen. So you need to know what each and everything does, right? And how basically it can make its move. So once we get to know the rules and the regulations of it, when you start moving it, the first pawn, when you move it, right, we humans, we think in such a way that the move that I make, I think about the opponent's move. It's not just only one move, the thinking that I'm going to do. So if I make this move, what will the opponent make his move, and corresponding, what should I do? So we keep thinking one after the other, and then only we start making the move. Why is that? Because we should make sure that we win the game, right? So in order to do so, we really think of, if in case I move my pawn from this position to the other position, what will the opponent take a move? Okay, and if in case I'm going to lose my pawn, what is the other strategies that I can apply? Yes, we think about it. So we observe the positions at the game, learn the model to produce better moves for the mission players, which is learned from experiences. So each and every move that we make in the board, we're going to make those as instances. We're going to make the system learn. We would have a set of training data to the system given, and upon the training data, it starts learning from the experiences which was being collectively given as an input to the mission. Okay, so this 1950, it was the first machine learning model by Samuel, who was working at IBM. He developed a program to play checkers. Okay, so basically, normally, if we consider ourselves, right, how are things learned from our side? Okay, if we have to learn something, how do we really learn? One is either we memorize it, right? We by heart. Our exams, what do we do, guys? We by heart it, right? So it's like we memorize things. Certain times, if you don't understand the concept and you're damn sure that the question might come in the exam, you start by hearting so that at least we fetch some marks, right? So we memorize it. So it's an accumulation of individual facts, We call it to be as a declarative knowledge. Okay, but basically it is limited by the time to observe facts and memory to store facts. If you don't have time to really study more in detail, you just keep mugging up few points in that, right? And even if you don't have memory to store, that you completely forget about it because you have just by hearted it rather than understanding it, right? So it's like the declarative knowledge, we normally call it to be as a memorization. Okay, so it's an accumulation of individual facts, and it is limited by the time to observe facts and the memory to store facts. When I tell generalization, okay, the second point over here that I'm going to discuss is basically the generalization over here. So when I tell generalization, deduce new facts from the old facts. It is an imperative knowledge, okay. So it's basically like I would have some old knowledge, okay. I would have had some previous facts about it, and I'm going to come up with the new things by actually considering my older. So like example, if I have to tell about this over here, so in case you're cycling, you'd have never forgotten to cycle, or you'd have never forgotten how to drive a four-wheeler if you have learned it, like. So maybe you will improvise yourself, but it's that when you start getting to know, okay, these are how, when you have to balance yourself, and when you have to pedal it, when there is something that's obstructly coming towards you, you start applying your brakes, you know the fact. The only thing is, maybe you can improvise it by telling, okay, if there's an obstacle that has come up sudden, so I have to maintain my speed in this way so that I can balance myself before something happens, So it's like from the older facts, I would get to know, like the deduce new facts from the older facts, but it is limited to the accuracy of deduction process. Essentially, it's a predictive activity. There are certain patterns, like you actually go ahead with certain predictions over here. There exist some patterns, and it assumes that the past predicts the future. Yes, right, this is obviously true in each and every in our day-to-day activities. The past predicts the future. Example, if I have to give a very good example, everybody would go to a grocery stores, right? Or we order a lot with Amazon, Flipkart, the lot of online shoppings that we do. So most of the time it gives you a pop-up telling that, man, maybe these are some of the similar products that you are willing, I mean, that you might like. Would you like to check it out? Why do all of that? Because based on our past shopping experiences, right, like the records that it has, it tries to find out the similar patterns among that, and those patterns which is very much coinciding to us, it starts projecting it to us, and it tells you, okay, these are the similar products that you want to check out. So if it is really required, like if you really wish to go ahead with, you can please have a check of it. And it also tells these are the products which are other customers as well checking with, maybe if you like it, please go ahead with it. Like it gives you, right? So it's a very generalized way of an imperative knowledge sharing. Okay, so that is with respect to how exactly the learning happens. Okay, so as I told you, these are certain examples that I've given for us. Okay, and Samuel, the researcher Samuel, he has termed ML as a field of study that gives computers the ability without being explicitly programmed. This is one of the very, very important definition, where there is nothing that is explicitly programmed. The mission is actually learning it. It has the ability to learn. So Samuel termed ML as a field of study that gives computers the ability without being explicitly programmed. I'll let you know what this is in few minutes, okay? But I want really to keep something in your mind, that it is not being explicitly programmed. Please have that a keynote in your mind: without being explicitly programmed. Okay, going ahead with the history of this, in 1960s, Russell Bolt proposed a perceptron. It's a very, very fundamental a unit for an intelligent systems. Okay, so it's with respect to a neural network, a single perceptron for a neural network. It was developed to illustrate the fundamental properties of intelligent systems with medical applications. So this was really, perceptron is the base of your neural networks. It's a complete base of your neural networks. I can tell it's a foundation. So each and every perceptron, how does it take an input? Because each and every perceptron has a main important a pre-activation and an activation function. Okay, we'll go more ahead in depth with your fourth module about artificial neural networks. So at that point of time, we will be dealing a lot with perceptrons. Okay, but the foremost thing over here is in 1960s, Russell Bolt was a person, was a researcher who actually came up with this perceptron, and he illustrated its basic principles, okay, with medical applications. In 1969, Minsky and Papert proved certain limitations. There were certain limitations with perceptron. It was not able to take up the data which is inseparable. It was not that performing well with the training data which is inseparable. So Minsky and Papert proposed the limitations of perceptron, where an XOR problem of perceptron could not be represented by a perceptron. Okay, you know what the XOR is, right? Yeah. So the XOR problem of perceptron was not able to be represented because the inseparable data could not be handled properly as specified. Okay, and in 1970s, a symbolic concept. Induction of AI. Okay, the symbolic representations of AI was come up. Okay, in 1980s, one of the very important algorithm of backpropagation. Uh, each and every neural network model that we consider with, they have the concept of this back propagation with updating its weights, in terms of gradient descent or gradient ascent. So even this topic will be detailedly going ahead with our fourth module. We'll be discussing this, but meanwhile here it's just an input that I wanted to give you. It is one of the very, very important algorithm, how to update your weights. I'll let you know what weights are, what bias are. These are the certain basic components with respect to artificial neural networks. Okay, so it was in 1980s, the backpropagation algorithm research big enough. And it is basically an advanced decision tree and rule learning, learning and planning and problem solving. It focuses on experimental methodologies. So all of these things were focused with during the year of 1980s, you know. In 1990s, you know, there were a lot of classification strategies that came up, like the SVM, the support vector mission classifiers, the ML, and a lot of statistics with respect to mean, standard deviation, variance, certain data mining techniques, text learning, reinforcement learning, and samples. These are certain more important topics. Again, we're going to discuss the decision trees in your second module, the linear and the logistic regression in the second module. In the third module, you have the support vector missions, you have Bayesian belief networks, and in your fourth module, you have your artificial intelligence. In your fifth module, you have all these reinforcement learning techniques, you know. So each and everything we will go in bits and pieces, you know. Let's go ahead with a smooth understanding of what machine learning, the subject, is about. Okay. But these were certain developments that happened in 1990s with respect to the support vector missions, ML statistics, data mining, text learning, reinforcement learning, and ensembles. Okay. In 1994, the first self-driving cars, you know, like they started the test with the first self-driving cars. In 2009, Google built a self-driving car. 2014, human vision surpassed by ML systems. Yes, a lot of image processing techniques, digital photographies, computer vision, with respect to artificial intelligence. You know, there's an enormous research growth that has happened with ML. Okay, so this is just a basic history of it, you know, the basic history of ML. Now let's actually go ahead and check out, okay, what exactly ML means. Samuel, why did Professor Samuel um, defined the term? It is telling that it is a field of study, okay, a field of study where the mission has the ability to learn without being explicitly programmed. Let's check out what does that mean. Let me give you an example here. um, when you know an algorithm, what do you do exactly when you go into your labs? When you go into your labs, you know, when you have given something to execute, what do? You have an input, right? You know, okay, you have the program that will be given to you, the algorithm or the logic of the program is known to you, if in case if you have to code also, but the logic of the program, if it is given to you, okay, so you know what are the inputs that you're going to pass to it, and you know the program, okay, you give it to the computer, you get the output of it. This is what you do it, right, in your lab program. If I have to highlight this, okay, so the first thing that you do over here, so let us consider this is the lab programming example. Okay, so what do? I come inside the lab. My teach or my coach is going to tell me the logic of the program. So I know the logic of the program to code, and I know what is the input that I have to parse. Okay, so the data that I have to parse is known to me. I come, I type into the system. Okay, so and finally I run it. I get the output. This is basically what our traditional programming is. This is what we have been doing from so far. Okay, what exactly happens with machine learning? Machine learning, what am I going to do is I'm going to give only the input and its output. Okay, I know the input of the program, I know the output of the program. I'm going to give it to the computer. Now I'm going to come up with a program for it. You remember the keynote that I told you, without being explicitly programmed. So I'm neither giving a program to the machine, okay, but the machine is going to come up with a program, the target function for me with respect to the input and the output given. Okay, so I have the training data, the input and the output. I give it to the system. The system will learn the input with respect to the given output, how exactly, and it would give me a program corresponding to it. This is what machine learning is. So ML explores the algorithm. It explores the algorithm. It learns or builds the model from the data. The data that I'm going to give is the input, right? So it learns or builds the model from the data, and those models are used for decision making. So this is what I'm giving to the mission. So I'm going to train the mission with the given data, right? And after training is done, I have to know whether, okay, So the given new instance, that new instance, the correct prediction is happening or not. Now I have to test the data, test whether my program, which is learned, is right or not right. So even with you, when we give you a subject, we deliver all the contents to you. But what is the task? So we are making you learn, but we have to quantify you, or we have to test you, right? So that's the reason we give you a test and an exam. It's just an example, guys. So if that's the case, then that's what we do here, right? So these models, again, also we have to test it to see whether it is correctly predicting whether the decision making is happening or not. So a similar criteria has been applied. So these models are used for decision making. So how does the model looks like? So here is a model that I'm just giving you. Okay. So ML explores the algorithm. How does it explore? As I told you, I would be giving the training data using my background knowledge. Certain things I've highlighted in red for your understanding. So training data using the background knowledge. So the background knowledge, I'm going to give all my training data. As I told you, my input as well as its corresponding output. Okay. I'm going to give that to here and I'm giving it to the model. Okay. Along with that, I'm going to give the experience or the data. As I told you, even I'm going to give the experiences as well, so that my machine will learn more better, right? So the experience data, I'm going to give it over here to the learner. So now what does the learner do? Okay, so the mission is having these components. So the learner is going to learn the system and it builds a model. Okay, the learner learns the system and builds a model. The input that was being given is the experiences as well as the training data in the form of background knowledge. So these two things are being given to the learner. So the learner learns the model and he builds a model to it. So once the model is being built, I have the model which has been ready based on the input and the output. I've come up with the algorithm. Now I have to check whether the model that I have built, can differentiate or can classify or predict any given problem. Okay, so what I do is I give a problem or a task for that. Okay, that requires a solution. So I'm going to give a problem or the task to this. Now, using this model, okay, the given problem or task is solved, resulting in a performance measure. And this red colored output over here is basically the learning output with an answer or the performance. Okay, so you can just imagine yourself this, the entire box is your mission. Okay, what you're doing is you're going to give the input data and along with that your output. So basically I'll consider one is the experience from past experiences, all the instances are being given. So I perform the training data using this background knowledge, so I'm giving it to the mission. So that's the input that I'm going to give. So now the learner learns or with respect to the input and the training data, entirely, and it builds up a model. Now, using this model, the reasoner for any given problem or task that requires a solution, he's going to come up with a solution for that. And that solution is going to be in the form of a performance metric. Okay. So learning output with an answer or the performance. So I'm going to get the performance metric. So this is how you actually make a machine learn with respect to machine learning. Okay, I think we'll stop here for today and we'll continue in the next classes with applications of machine learning, which is one of the very important topics in our day to day. Okay, thank you so much, guys. See you in the next class. Bye.